Hello, this is Mrs. Bauman, and today's lesson is from Chapter 3, Lesson 4 on linear programming. Big picture, what we're trying to do is find a maximum or minimum of some quantity that satisfies our problem or our objective. We will define an objective function. What do we want to maximize or minimize? What are these quantities or variables that need to be modeled? We need to define the constraints. What are the limits on our variables? How much of a quantity do we have to work with? The feasible region are all points that satisfy all of our constraints. Again, we'll be looking for an overlapping region. We are going to find the vertices. These are the intersection points where our lines meet. These are sometimes called critical points or the corners of the feasible region. We will test these vertices in the objective function to find the desired max or the minimum. When testing the vertices, in this order, we want to graph our constraints, find the coordinates for each vertex, the intersection points, and then we will evaluate each vertex in the objective function to find the max or the min, depending on the problem. We will first begin by practicing the last part of the problem. In this case, example 1 wants us to find the maximum p for the objective function p equals 3x plus 2. What is the value of p at each vertex? In this first example, it has given us a system of constraints. We will again label these 1, 2, 3, and 4. In our first equation, we have a slope of up 3 over 2 and a y-intercept of 0, negative 3. So in our first equation, we will start at negative 3. We will go up 3 over 2, up 3 over 2, up 3 over 2. Notice it's a greater than or equal to, so we will have a solid boundary. And in this case, it wants us to shade above. Instead of shading, I'm just going to put little arrows at the end of our boundary line, noticing that we're supposed to shade above. In our second equation, our slope is negative 1. So we will go down 1, run to the right 1, and 0, 7 is our y-intercept. Plotting 0, 7, down 1 over 1, down 1 over 1, down 1 over 1. We notice that intersection point. Again, we have a solid boundary. And in this case, it wants all y coordinates less than the boundary. We will indicate that by arrows at the end going down. Our third and fourth equations are vertical and horizontal boundaries. In 3, I want all x coordinates to be greater than or equal to 0. Again, I will note this with arrows at the end. And in our fourth boundary, I want all y coordinates greater than or equal to 0, so above. Again, in our first equation, we'll label that 1. That's the boundary. The second boundary, the third boundary, and our fourth boundary. If we put our pencils on these boundaries and use that to drop or go above to shade, we will notice that the feasible region, we need to be below this line, above this line, to the right of the vertical line, and above our horizontal line. So our shaded region is that quadrilateral that's shaded. Our critical points are the vertices, the points of the shaded region. So I'm going to circle those. Our intersection points on this is 0, 7, 4, 3, 2, 0, and 0, 0. I'm going to label these A, B, C, and D. We will now evaluate each vertex in our objective function to find the maximum. Again, we're looking for the maximum P. Maybe this stands for profit. If we evaluate for point A above, our profit is equal to 3 times 0 plus 2 times 7. I'm substituting the x and y coordinate for point A, that vertice, which results in 14. For the second point, which we called B, our profit is 3 times 4 plus 2 times 3. 12 plus 6 is 18. For our third point, our profit is 3 times 2 plus 2 times 0, which equals 6. And finally, our fourth vertice, which is 0, 0, when we substitute it into our objective function, three times 0 plus 2 times 0 equals 0. Again, we're substituting these points into our objective equation. We notice that 18 is the maximum. So our answer is 4, 3 has a max of 18. This is the back end of the math that we will do on our backside full problem. In example 2, it wants us to find the values of x and y, in this case that minimize c. Our objective function is c equals 1x plus 3y. Again, our constraints, our inequalities that we're given, we are going to label those 1, 2, and 3. In this case, we have 3 inequalities. We're going to rewrite the first inequality in slope-intercept form. 1x plus 2y is greater than or equal to 8. I'm going to subtract the 1x from both sides. 2y is greater than or equal to negative 1x plus 8. Divide every term by 2, and we have y greater than or equal to negative 1/2 x plus 4. If I plug in 0 into the inequality, I would get y greater than or equal to 4. In other words, 0, 4 is a point on the boundary. Down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. You can always create a table if you do not recall how to graph using slope-intercept. This is our first equation, and it wants all y values greater than. So I'm going to put a little arrow towards the end. We want all points above that boundary. Our second equation's boundary is x equals 2. Recall that x equal equations are vertical lines, in this case our boundary will be a vertical line, x equals 2, and we want all x coordinates greater than that boundary, so we're going to go to the right of that boundary. In our third equation, y equals 0 is our boundary. Recall that that is a horizontal line, the x-axis. All y values greater than or equal to 0. Again, I'm going above that boundary. Putting your pencil on all three, I need to be to the right of my vertical, above my slanted line, and above my horizontal. This is my feasible region. My points of intersection in this case, again, are where our lines intersect. And in this case, we only have 2. Just because the coordinate plane stops on our paper does not mean our points stop. And this region continues on. We only have 2 intersection points. In this example, 2, 3 is our intersection, as well as 8, 0. Again, we'll label these A and B. In our third step, we will evaluate these points. For A, our objective function again is c equals 1x plus 3y. So using our first point, our c would equal 1 times the x coordinate, which is 2, plus 3 times my y coordinate, which is 3, and 2 plus 9, 11. Using our second point, c equals 1 times 8 plus 3 times 0, which equals 8. Again, we're looking for the pair that minimizes c. In this case, it is the point 80. So in this case, 80 has a minimum of 8. On the back side of our notes, we will do a complete problem. We're going to use linear programming to solve this real-world problem. In our example, let's read through it quickly and highlight the given information. We will define our variables, write our objective, write the system of inequalities, graph them, find the intersection points, and identify the one that satisfies the problem. Question in this case, we are going to maximize a profit. Looking at our problem, it says we have a tray of corn muffins, 4 cups of milk, and 3 cups of wheat flour to make a tray of corn muffins. The tray of bran muffins takes 2 cups of milk and 3 cups of flour. The baker has 16 cups of milk to use and 15 cups of wheat flour. He makes a $3 profit on the tray of corn muffins and a $2 profit on the tray of bran muffins. How many trays of each type should the baker make to maximize his profit? There are a lot of numbers. We're going to work backwards by first identifying what is the point of this problem. They want to know how many trays of each type the baker should make to maximize his profit. That is our objective. Well, how many trays of each type? We will first define our variables. What is he making? He's making trays of corn muffins and bran muffins. We're going to define x as our number. All of your variables in linear programming are quantities or numbers. You need to include the number sign or write the word number. The number of trays of corn muffins. And let's y be our number of trays of bran muffins. Our objective, what is our point of this? To maximize his profit. So we're going to let P be profit in dollars. So our objective function or equation is P equals. Well, let's look back through the problem and identify our profit variables. $3 profit for the corn muffins and $2 profit for the bran muffins. So $3 for our corn muffins, so profit is dollars. $3 times the tray of our corn muffins, X, plus $2 profit for each tray of bran muffins, which is Y. We have now identified our objective function. Now we need to write our constraints as inequalities. In our system, we're going to work backwards much like we did for linear inequalities. We go up through our word problem. What are our constraints? What are the values of resources he has? He has 16 cups of milk and 15 cups of wheat flour. So we're going to work backwards again. He can use no more than 16 cups of milk. And it's important to label these. Everything to the left needs to be talking about milk. And he could use less than or equal to up until 16 cups of milk because that is what he has for resources. He also has 15 cups of flour to use. He can use no more than that. Working backwards on the left-hand side for 16, let's look for milk as it relates to the corn muffin trays and the bran muffin trays. So let's highlight our milk. We have 4 cups of milk required for the corn muffins and 2 cups of milk for the bran muffins. So we will write 4 cups required for our corn muffins, which are X, plus 2 cups required of milk for our bran muffins, so 2Y, milk, milk, milk. Now we will go back and look for our flour. We need 3 cups of flour for our corn muffins and 3 cups, the same amount, of flour for our bran muffins. So 3 cups of flour for our corn muffins and 3 cups of flour for our bran muffins. 3x plus 3y has to be less than or equal to 15 cups of flour. Now in the real world, we cannot create negative quantities, so we will always add the 2 real-life constraints. Our x, the number of corn muffin trays, must be greater than or equal to 0. I'm going to put a semicolon, and our y, the number of bran muffins, also has to be greater than or equal to 0. These 2 add-ons are called real-life constraints. If they do not tell us we have to make at least a certain amount of muffins of each type, we will always add greater than or equal to 0 for both of those quantities. Now we are going to carefully graph those. I'm going to label them 1, 2, 3, and 4. Notice that there isn't a coordinate plane in this example. Well, that is because of our real-life constraints. We can add for our x value, our number of trays of corn muffins, we know we have to be bigger than 0. And since y is representing our bran trays, that also has to be greater than or equal to 0. So in real life, most of the time, we will be graphing our inequalities in the first quadrant. And we'll just include a coordinate plane box for that, so we can write or draw a little larger to identify our intersection points, our critical points. Well, to graph equation number 1, we might want to consider rewriting this in slope-intercept form. 4x plus 2y has to be less than or equal to 16. Subtracting the 4x from both sides, 2y is less than or equal to negative 4x plus 16. Dividing by 2, we have y is less than or equal to negative 2x plus 8. This is our first equation that we're going to graph. Our y-intercept is at 0, 8, and we have a down 2 over 1 for our slope. I'm going to go ahead and use two boxes to represent 1. 1, 2, 3, 4, 5, 6, 7, 8. If I am going to jump by 2 boxes for a quantity of 1, we should always use the same interval on our y-axis so we can clearly identify the correct coordinates of our intersection point. As long as our intervals are the same, we can use each box for down 2 over 1. Down 2 over 1, down 2 over 1. And we are going to draw the points for our first boundary. We're going to connect this. Again, it's a solid boundary because of the less than or equal to. And I know that I'm going to be to the left of this because I want less than or equal to. For our second equation, we have 3x plus 3y is less than or equal to 15. We are again going to subtract our 3x. 3y is less than or equal to negative 3x plus 15. Dividing by 3, we have y is less than or equal to negative 1x plus 5. That is our second equation in slope-intercept form. So we have a y-intercept of 5 and down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. It looks like this is the intersection. And we will continue that graph. We will connect the inequality. Again, using our understanding of graphing inequalities, I need to be below both of those lines. Well, if you put your pencil to be below both the line that has the intercept of 8 and 5, I need to be below both, so I know I need to be below this portion. I also need to be below the other equation, so I am over here. I need to be above the vertical line, x greater than or equal to 0, and I need to be above y equals 0 because y needs to be greater than or equal to 0, our real life constraints. This is our feasible region. Notice I do not have those triangles shaded. The feasible region needs to satisfy both. Our intersection points are circled. What are our intersection points? Well, I'm going to start with the first one, which is 0, 0. I'm going to call that A. For B, it's 0, 5. Be careful that you do not write 5, 0. The third point is at 3, 2. You need to be careful. Don't just count the boxes. 3, 2. That is our third point. And our fourth point is at 4, 0. Be careful with the points that are on the X or Y axis and make sure that you have your points written correctly. We are first going to test A into the objective function. Remember, looking above, our objective function is to find maximum profit. So P equals $3 times our number of corn muffins, which is 0. So 3 times 0 plus $2 for our bran. Well, this profit is 0, clearly not our maximum. For point B, we have 3 times 0 plus 2 times 5 for $10. For point C, P equals 3 times 3 plus 2 times 2, 9 plus 4, 13. And finally, testing our 4, 0 point is 3 times 4 plus 2 times 0 equals 12. 13 is our maximum. So our profit is maximized when the baker makes 3 trays, and that's our X, of corn muffins and 2 trays of bran muffins for a maximum profit of $13. This is the end of today's lesson.